So, okay, for number 7 it says a certain amount of protons, a certain amount of neutrons bind together to form a single nucleus under the influence of the strong nuclear potential energy curve shown. Neglecting electrical interaction, the total mass of the final state is. So to do this, we're going to have to find energy. So basically, we kind of have an energy to start with, where we have it's given that rest mass of a proton equals 938 mega electron volts per c squared, and then neutrons are 939 mega electron volts per c squared. And so there's 2 ways he could do this. So he could either do one of those weird potential energy curves in which he gives you, this, basically dip, and whatever. This is supposed to be like 3 Fermis, and this is supposed to be, like 6 mega electron volts. He could either do that, or he could give you that graph where you have that kind of big sweeping kind of curve where it gives you binding energy per nucleon. So do you guys know what the 2 things I'm talking about are? Okay, so if he gives you a binding energy per nucleon, this should be pretty easy. In which case, he'll just give you a value of basically he'll just expect you to look and see, okay, we're forming this. So in this case, we're gonna take 2 protons and 2 neutrons and form helium. And he's gonna basically just say, so these start with a binding energy of 0. And then if you have helium, the binding energy per nucleon is 7 mega electron volts, as we kind of did in class today. So if he does that, all you're going to have to do is just multiply 7 times 4 to get the amount of energy that was released. And then you're going to, then you'll have the, then you'll just basically, let's see. Then you'll take the amount of energy that you had to start with all 4 of them, subtract the number that you lost to heat by having this binding, and then convert that energy into mass. Okay, so he hasn't done it in mass, so I don't know why he's doing it now. But the other way he could do is he's going to give you basically some sort of drawing in which, so I'm just going to show it as kind of. So for helium, the easiest way to draw helium is basically, like he said, there's 3 different little, balls, and then one is put on top of those 3, so it forms a little pyramid. So every single ball is touching every single other ball. So in that case, you just have to count the number of strong nuclear force attractions there are. In which case, basically, you can say, that ball number 1 touches 2, 3, and 4. So that has 3 different bonds. Number 2 also touches them all, but since you already counted the bond that it has with 1, you only have to count the one that it attaches to 3 and 4. And then same thing with 3, it attaches to all 3 other ones, but you already counted the other 2, 1 and 2. So it's just that bond between 3 and 4. And that basically gives you 3 plus 2 plus 1 equals 6 kind of bindings. If you did the homework in the last few days, then you'll understand what I meant by bindings. And you'll just take the number of bindings total and just multiply it by the potential energy per binding, which will be given by this sort of curve. So does everybody understand what I've said up to this point?
What's the curve thing going to give you?
The amount of energy that you get per binding.
So it's 6 here.
Yeah, I just made it
okay.
6. I made it 6. So I think from what, I don't know if...
That would give you the binding energy per nucleon.
Yeah, that would give you the binding energy per nucleon.
Yeah, and then once
So it'd be 36 binding in it?
it'd be 36 total because you'd have this is the amount per binding. That's the potential energy that you'll get out per binding.
Okay.
Yeah. So this is the energy that you get per binding, and so you multiply this by the number of bindings. And the other way, you'd have a certain amount of nucleons and a certain binding energy per nucleon, in which case you'll just do nucleons times binding energy. So do you understand how we're doing that?
Okay, so how do you convert that to math?
Yeah, using E equals mc squared.
Oh.
So yeah, so we're gonna do this in just a second. So I was just making sure everybody understands the two ways he could do this problem. I think he's doing it this way. From what it sounds, if you read the problem, I think it sounds like that, but I really have no idea. I'll know tomorrow. But to do this problem, I believe what he's wanting you to do is basically just take the 2 protons and 2 neutrons. They have a certain amount of energy to start with before they bind, and that is 2 times 938 mega electron volts per c squared, plus the 2 times 939 for the neutrons, mega electron volts per c squared. And so this is the amount of energy that you'll have before they bind together. As individual nucleons, they'll have this much energy. Technically this much.
2354.
2354. 2354 mega electron volts. Okay. So if he gives you this, what you're going to do is determine how many bindings there are. So in this, I already told you you have 6 bindings, and I gave you, once again, this was 6 mega electron volts. You get 6 mega electron volts per binding.
I think it's 3754.
Yeah.
3754?
Yeah.
How did I do that wrong?
3754?
Yeah.
Okay. Thank
Sorry.
you.
Oh. Yeah.
Not trusting you anymore.
I did
Kidding.
239.
Okay, so 3754. So wow, that's really bad. So okay, so that's before you bind. Okay, but now you have 6 bindings, and we're gonna say that it releases 6 mega electron volts per binding. So in that case, you're going to just take this number 3754 and subtract it by that the 6 bindings times the 6 mega electron volts per binding. So in this case, it'd just be 3754 minus 36. What do we have then?
3718.
3718. Okay, so 3718. Okay, so this is the amount of energy that you will have in this molecule, this one hydrogen atom, after it's bound together. And so now we can use the E equals mc squared. So now we have 3718